Okay, so you've become a little bit acquainted with e, and now let's tie this in with our exponential functions. Exponential functions with e as a base have the same properties as functions you have already studied. The graph of f of x equals e to the x is like other graphs of exponential functions, just like f of x equals 3 to the x. The domain for e to the x is all real numbers, and the range is the set of y values where y is greater than 0. So in our graph, still e to the 0 is 1. E to the first power is that 2.718281828 and so on. So there is our parent function graph. It's a good idea to know what that looks like. So if we switch that around and instead of looking at the exponential equation, and if we look at the logarithm with the base of e, this is called the natural logarithm, and we abbreviate it ln rather than writing that log base e. So e gets its own special treatment. Instead of writing log base e, we're going to write ln. Okay, natural logarithms have the same properties as log base 10 and logarithms with other bases like 4 or 8 or whatever. The natural logarithmic function f of x equals ln of x is the inverse of the natural exponential function. So remember, if we had 4 to the x, then its inverse was log base 4 of x. So since e is just a number and ln is log base e of x, its inverse is e to the x. Inverse, of course, remember on a graph, looks like the reflection of the same graph over the line y equals x. So in blue you can see e to the x, and in red you can see ln of x. The domain and range, since it is for the natural logarithm, since it is the inverse of e to the x, its domain and range will switch. So the domain is the x value is greater than 0, and the range is all real numbers. All of the properties of the logs from 7-4 also apply to the same logarithms here, such as seen at the bottom here. If we were to simplify each of these expressions, if we had ln of e to the negative 2t, remember whenever we had things like log of 10 to the third, say. Well, log base 10 of 10, essentially this cancels and you would just be left with the 3, so that would equal 3. So now that we have ln of e to the negative 2t, ln and e cancel each other, since remember that is log base e of e. So that would cancel, and you'd just be left with your exponent of negative 2t. Whenever we saw things like 4 to the exponent of log base 4 to the x, well, if we saw that, we knew the 4 and the exponent of log 4, basically they canceled, and you were left with the x. Similar thing here. E to the log base e, or to the ln, cancels, and you're just left with the t minus 1. And finally, we have e to the power of 5 times ln of x. Before we can just cancel things away or out of the equation, we should make sure there's nothing in front of the log. So this 5 right here, take that, and we'll need to move it back as the exponent for the x. So e to the ln of x to the 5th, e and ln cancel, left with the x to the 5th. Let's look at an economics application. What is the total amount for an investment of $1,000 invested at 5% for 10 years compounded continuously? There's some keywords here, and they are compounded continuously. So we've looked at compounded quarterly, yearly, weekly, daily, monthly, whatever, but we haven't used this word continuously yet. That word continuously is the key word to tell us that we are using a new formula here, and it's A equals P times E, that number E, to the RT. It looks like A equals PERT, but it's not really PERT. Okay, so we have A is going to be our final amount. P, just like it's always been, is going to be the initial. There's our new friend E. Here's going to be the rate in decimal form. And T is going to be our time. So let's look at this example. We are investing $1,000 at 5% for 10 years compounded continuously. So we're looking for what that final amount will be. So we'll have $1,000, so there's our value for P, times E. Our rate is 5%, so that's 0.05, and our time is 10 years. At this point, you could just take that, plug it into your calculator, and you'll get A equals 1648.72. So, after 10 years at 5% interest compounded continuously, $1,000 will become a happy $1,648.72. Now, I have this sneaking suspicion that you're just thirsty for more knowledge here and you're thinking, Mrs. Suderman, give me some harder problems. Okay, well, not harder problems, but maybe just more interesting. Let's look at some half-life problems. The half-life of a substance is the time it takes for half of the substance to break down or convert to another substance during the process of decay. Natural decay is modeled by the function below. So don't let this scare you, because really this is a whole lot like something we just looked at. You know how we had A equals P times E to the RT? Well, A is now N of T, the amount remaining. The amount we started with, this N sub O or N naught, is what used to look like P. Then we have our E. Notice we've got a minus sign. That's because we are decaying, so that's always going to be negative in the equation. But K itself will not be negative. K is the decay constant, kind of like what our rate used to be. And then T is the amount of time. Let's look at how to use this. A paleontologist uncovers a fossil of a saber-toothed cat in Bexar County. He analyzes the fossil and finds that the specimen contains 15% of its original carbon-14. Carbon-14 has a half-life of 5,730 years. Use carbon-14 dating to determine the age of the fossil. Pretty cool. Let's do it. We'll have two steps here. First, we'll need to find the decay constant for carbon-14 since it was not given to us. And then we'll use that value to solve for T. So just a reminder, that function that we just learned was N of T, our final amount, will equal our original amount times E to the negative K, our decay constant, times T. So, whenever you are looking for the decay constant and you are given the half-life, this part is a little strange to think about, but don't overstress it here. We'll compare what we used to have, the 100%, to what we have now, which is 50%, or half. Since we're looking at half-life, we're looking at how long it takes to get to half of what we used to have. So, if we're looking for how long, or what is our decay constant for whenever we have a final amount of half of what we used to have. So if we had 100%, here's at 50%. Then we'll have E, we're looking for K, and the equation, or the problem told us that the half-life was 5,730 years. So our function is saying here, at 5,730 years, depending on what our K is, we'll get from 100% of what we used to have to 50. Okay, so we'll have 0.5. Let's just rearrange this a little bit so that way it's a little simpler. Okay, so 0.5 equals E to the negative 5730 times K. Don't forget that. Okay, I'm going to go ahead and take the ln of both sides, the natural log of both sides. As we just talked about, ln and E cancel, basically, and you're left with that exponent. So we have ln of 0.5 equals negative 5730 K. To get K by itself, we'll divide both sides by that negative 5730. Then we can take this stuff right here, plug it into a calculator, and you'll end up that the decay constant is about 0.00012. Okay, so we're halfway there. We found out the decay constant. So we used up this half-life information, but we are trying to figure out how old is this fossil. We've only figured out the decay constant for carbon-14. We haven't even looked at the fossil yet. So let's take a look at this fossil. We know we have 15% of the original amount of carbon-14. So we have 15% currently. Here's that final amount. we used to have 100%. Here's the E. We know that K is this, don't forget that negative goes there, but the K is the 0.00012, and we're looking for the amount of time. So again, if we just want to simplify this a little bit so it's not so scary, I mean, taking out the 1 doesn't really change anything. Anyways, let's go ahead and take the ln of both sides, just like we did before. We're following the same process. 0.15 equals, so whenever we take the ln of both sides up here, the ln and the e will cancel. And we'll just be left with that negative 0.00012 times t. To get t by itself, divide it by this crazy long decimal. Are you tired of writing that yet? Negative 0.00012. And the fossil is, are you ready for this? About 15,809 years old once you have plugged that into the calculator. Pretty old, but there you have it. Okay, done. Are you feeling okay? Did you make it? You have survived the lesson on natural base E. See you later. Bye.